Hi, in this video, we're going to take a look at handling imbalanced data when I'm fitting a logistic regression model. All right, imbalanced data is a situation where the proportions of my data just are out of whack for some reason or another. And so we're going to talk about ways to address this, ways to handle it. So, there are going to be times that our data is going to contain too little of a particular level of a field that we want to have more of. And this is the largest problem when it's the target variable, but it can also be with our independent variables also. And so, how we handle this is going to be very important. I'm going to go over some techniques, some tools to tackle this. I'm going to tell you what my personal opinion of our preferences are of those. All right. So first and foremost is that we have a classification problem where one or more levels are so rare in the data that the other records drown out the rare level. So imagine a situation where I'm trying to model like a rare disease, like a really, really rare disease. And it's super rare. It doesn't happen very often. And I go out, I collect my data. I have 99.99999% of my data is no disease, and then I have a small number of records for the actual disease. Well, now in this situation, this is actually isn't a problem with my sampling. This isn't a problem with my data. This is just reflecting reality of what's going on. But when I go in to fit the logistic regression model or any other supervised learning model for this, what's going to end up happening is that the frequent levels are going to drown out the low frequency levels. And so, in this particular case, the actual disease cases of the rare disease will just be drowned out, that the model really doesn't pick up anything for it. And so the model will be reflecting reality because it's such a rare disease. But that would be defeating the purpose of having the model. And so what we want to do is make some kind of adjustments on here. And so in this situation, there's no problems with our data. It's just that the proportions are so skewed that the level that we're really interested in just isn't there. All right. Now, the next one is where our dependent variable, our target variable, the proportions do not reflect the known population distribution. So let's say that I know that, let's say 10% of the cases should be positive. And I go out, I collect my data, and I see, oh, 1% of the cases are positive. But I know from subject matter knowledge, from experience, from previous studies, something like that, that it should be 10%. Then I'm like, well, that's a problem. I know that I've got too few. Now, I could also have too many, and the techniques that we're going to talk about can actually be used to make corrections in the same way. So like, let's say I had that 10% case, and I know I'm supposed to have 10% of the positive case, but when I go out and I do my sampling, I end up getting 25. Well, then I need to make an adjustment also, but in the opposite direction. So in this situation, our sampling does not reflect what we know it should look like. And of course, if it doesn't look like what we know it should look like, either our knowledge is wrong or we've got a problem with our data. Either way, we need to make an adjustment. Dealing with your knowledge, if it's wrong, I can't really help you there, but I can talk about ways to help with your data. Now, the last one, and this one does not get enough attention. This is where our independent variable, one or more of them, do not reflect a known population distribution. So let's say from the census, I know that 20% of the population is African American, that when I go out and I sample. Well, I go out, I collect my data, and you know what? I've got under 5%. I actually had this particular situation happen at work for me, that a survey was sent out, and I knew that approximately 20% of the families that were sampled were African American, according to the demographic data that I had. And when I got the surveys back, the African American community didn't respond to my survey. What do? I had to make some choices, had to talk about the problem with stakeholders, make sure they understood what was going on, talk about potential ways to address this, and then proceeded with how they felt was the best way to go. Ended up upsampling those observations in that particular case because they felt that that was acceptable. All right, now I'm going to talk about the ways that we can adjust imbalanced data, and I'm going to put it in order of preference. So the first one is the one that I believe is the most important. The last one is the one that I think you should avoid as much as possible, but it's still a tool in our tool belt. All right, so the first one is going to be to adjust the weights of our observations to reflect the desired distribution. All right, adjusting your weights is a neat trick for handling problems. A lot of problems in like linear regression, and it can also be used to address problems with like imbalanced data. And so, I like this a lot. Why? Because when you adjust your weights, you're taking full advantage of your data. You're using every single data point that you've got. You're not excluding anything. Also, you're not like, repeating anything with the upsampling. Upsampling is effectively, adjusting weights also just in a different manner. And there's no like fake data going on. And so, this works out very well. This is adjusting weights is a very powerful technique. Now, a misconception about adjusting weights is that some people will say adjusting weights will improve your accuracy. No, adjusting weights change where your errors are. All right. And so you're basically just moving errors around with how that works. That's a common problem that I bump into. Adjusting weights, if I'm going for pure accuracy on my raw data, leaving things alone is the best way to get the best accuracy because it's optimized to that level. So adjusting weights, what I'm doing, I'm shifting the emphasis to the low frequency levels to get the desired balance that I want. Now, the next one is going to be cost-sensitive learning. So here we're going to adjust our loss function to increase a penalty for missing on the low frequency levels. Scikit-learn does this very well, R does not. We can effectively use our weights to achieve the same goal off of this, but it's a little bit more technical. I'm not going to cover this here because I'm using R. Scikit-learn supports this much better than R does. Now, next one is downsampling. I've used this one quite a bit professionally. And so here, what I'm going to do is let's say I've got two levels, and this level is low, proportionately low. This one is high. Well, what I'm going to do, I'm going to randomly filter out some of the more frequent level observations until I get the right balance. The reason why I like this one is that I don't have to worry about the same problems I have with upsampling. I don't have any fake data floating around, and downsampling gives me a smaller sample, which will improve computation time. So, it's a win-win all the way around. Now, the next one is upsampling the low frequency level. So downsampling is where I get rid of the high frequency level observations to get the right balance. Another thing that I could do is I could upsample where I sample with replacements the low frequency level observations. And so let's say I have five observations for a level. What I could do, I could randomly sample with replacement just these five over and over and over until I have the right balance. And now, something that's sticky about this, with upsampling, I have to do this after I do my data set partitioning, because if I upsample first and then I split, I will almost guarantee that you will have observations that their duplicates are across your partition and which defeats the unseen aspect of your partition. So I would, upsampling is low on my list, but it's still one that I've used professionally for certain situations. Now, this one is very popular with those who have stronger like computer science backgrounds, especially SMOTE. I feel like this doesn't deserve the popularity it gets. There's a lot of academic papers about it. I encounter this at work, those who have stronger like computer science backgrounds. But I feel like this really isn't considered in the light that it should be. So here, what we're going to do, we're going to use an algorithm of some form to take the low frequency level observations, and we're going to use them to generate new observations. And so these are synthetic fake data. And so the reason why I don't like them, first and foremost, they're fake data. Also, we have problems with our partition. Even if I do it before or after, I'm going to have problems with my partitioning and synthetic data. Now, the next one is one that I have used when I was just desperate for data. When I had very, very low frequency, very, very sparse data on the low frequency observations. In that case, repeat those across your training, your validation, and test set. You shouldn't do that. It completely contradicts the idea of unseen data on validation and test, but sometimes we just don't have a choice. Sometimes we don't have, sometimes we're just desperate for what's going on. We gotta get a result, gotta try something to get a good model going. If it's a good model, but I don't have validation and test set statistics that I can trust, it's still a good model. So consider that. The goal is to build a good model. The goal is not to know that you have a good model, it's to actually have a good model. So if you follow solid principles and you proceed forward, telling your stakeholders that you're on shaky ground, that might be all right. You have to judge the situation for what's going on. All right, so now something to consider when we have imbalanced data is our method of balancing the data and our partitioning of our data set. So I can adjust my weights before or after I split my data. That's not a problem. So this is a nice aspect of weights. Doesn't really, assign the weights across accordingly. It's not going to impact anything. And we can choose to use the weights in our calculations of our metrics, or we can just go with the raw version. It's up to us. It depends on your project. This is another nice aspect of using weights. Now, downsampling, I can downsample before or after splitting the data. I prefer to downsample before I split my data, but it would be reasonable to do either way. Upsampling, now this one must be done after we split our data. Okay, so if I upsample before I split, I am practically guaranteed to have duplicate observations across the partitions. And so if I have an observation in the training set and its duplicate is in the validation, and or a duplicate is in the test set, then those duplicate observations are killing the unseen aspect of validation data, test data. And so what I want to do instead is split my data. After I split it, I run upsampling on my training data. If I want to, I'll do upsampling on my validation data. If I want to, I'll do upsampling on my test data, and then I can proceed. Downsampling, it doesn't matter. We can do it before or after. Upsampling, we must do it before. Now, the next one, generating synthetic data, we have problems either way we go. Okay, so if I generate synthetic data before partitioning, then what I have done is at somewhere in this process, I've taken a data point that's ultimately in training, a data point that's ultimately in validation, and then I created a synthetic data point. Now, if that synthetic data point is inside the training set, then what's happened, that synthetic data point is like repeated effectively because it's influenced by the validation data. The validation data had some impact on that data point. Therefore, we are contradicting the unseen aspect of our validation data. And so this is definitely an aspect that we don't like to have. So you can go, you know what? I'll go ahead and generate synthetic data, after I do my partition. Okay. Well, then what you've done is you've taken the situation where you had very little data, you had less data that you wanted, and you set it up so that you had even less for the purpose of synthetic data. So you made the situation worse to avoid the duplicate aspect across your partition. And so you can't win. This is why I don't like synthetic data. It's a good choice if if the other situations aren't appropriate for you, maybe you can be using a model structure that doesn't allow you to adjust weights. Maybe I have very, very, very little, to the point where upsampling really wouldn't even make sense, because it would just be duplicating the same few values over and over and over. And so synthetic data, can step in well when I have very little data. But this comes at a cost. I would say there's the academic papers that I've seen put more of an emphasis on SMOTE than any other, but it's a tool in our tool belt. I would say avoid it. Now, one thing about dealing with imbalanced data, I don't have to balance my test set. I don't have to balance my validation set. I don't even have to balance my training set. I could just balance validation or test, depending on my problem. More than likely, you're going to balance your training data. Now, when it comes to validation and test statistics, I need to make a choice on balancing the data, because it's going to change my statistics if I do, depending on what I do. If I don't balance my validation set, if I don't balance my test set, and I take my statistics, well, the training data doesn't look like the validation data. And so my statistics are going to look worse if I don't balance the data. Now, if my goal is to have it so that my model is, if I want it so that my validation data and my test data show me how it's going to perform on the data that's going to be coming in through the scoring. So if my data set, my sampling reflects the actual true population, and so in that situation, the validation and test data should be left alone, because the accuracy there is the accuracy I'll get down the road. Now, I'll have an inconsistency between training and validation, training and test. You have to make a choice. Either your validation and test data are going to look like your training data, not like your population data when you go score it, or your validation data and test data will look like your scoring data, but not like your training data. You have to make a choice on it. Do what's best for your project. One thing to remember: models always look like their training data. Period. Models always look like their training data. If I change the proportions of my target variable, I'm going to change the proportions of my predicted values. And so the results will look like the training data, guaranteed. All right, so let's go ahead and run through this. I'm going to set up my workspace. I want to limit the number of printed values, avoid scientific notation. I do some stuff with piping that the tidyverse doesn't like, the contemporary tidyverse doesn't like. Make sure there's no gunk in my workspace, and I like piping, so I'm going to do that. Now I'm going to use the German credit data set from the Carrot package, and I'm just going to go through and do some data prep. So I'm going to just work through and set things up. All right, now something about this is that the dummy variables are set up for us in this data set. If I don't want that, then what I'm going to need to do is go through and combine them depending on what data prep I choose to do. What you do and how you tackle it is up to you. It's not really important for this. Here I'm going through and I am setting it up so that categorical variables have their frequency. It determines the frequency of the factor. And so the most frequent one is first, second most frequent is second, and so on. And then I'm going to lump all of so if I have like a bunch of sparse values, I'm going to just clump them all into other. And so this will help prevent overfitting by making sure that I don't have a bunch of sparse dummy variable columns. Remember, the more predictor variables I have, the more prone to overfitting I am. And so because of that, I don't want a bunch of just extra sparse columns, dummy variables floating around. And so here I'm just going through doing some data prep. We've got duration, amount, installment rate, percentage, residence. We have Now here, here's our target variable of class of either good or bad credit. Here is our checking count status. And you'll notice I've got other is the least frequent level every single time. So we had other, so other is everything that wasn't in these three. So now here, everything is in paid duly or the other category. And we have our employment duration, our housing, and you'll notice that things are, I don't have any like crazy sparse levels off of this because I did the other. Well, this is rather low, but it's not too bad. All right, so first thing I'm going to do is I'm going to look at my bad credit, good credit ratios. Now, something about this is not imbalanced data. This is truly not I mean, it is and it isn't. When you start having a 2-to-1 ratio or greater than 2-to-1, so 3-to-1, 4-to-1 in your ratio of observations, you will start seeing a degradation of some of your model metrics. And so around 2-to-1 and greater is where you start seeing a shift in how certain metrics just pick up aspects of your model. And so in that aspect, if I have a 2-to-1 ratio, 3-to-1, 4-to-1, anything greater than 2, then I will, there's to some degree an imbalance. But in real life modeling, this is not imbalanced. In real life modeling, this is not a problem. If I've got 10%, honestly, there's plenty of cases where I have to slug through, and I've got only 10% for the low frequency level that I have to deal with. But that ratio proportions is something that I need to be mindful of when I look at my statistics. So here, this isn't, in my opinion, this is not imbalanced data. But I'm going to use this data because it's pretty concrete, pretty easy to work with, easy numbers to interpret. And I don't have, so if I had like very, very, very few, imagine if I only had 3 bad credit observations. Well, in that case, I would be like severely, severely imbalanced, and it would be very hard to get a decent model. It would be really hard to get a model worthy of being put in production. All right, so I'm going to fit a baseline model. I'm not going to change anything. I'm just going to fit it. I'm going to launch it. Honestly, in real life industry, these proportions are fine to just fit the model and run with it. But I'm going to go ahead and proceed as if this was a more severe case and dealing with what I can. So adjusting the weights is my preferred method for dealing with imbalanced data. It takes full advantage of our training data. Is really the least cumbersome way to go about it. It's well supported by a lot of functions, and it's supported from a theory point of view. I mean, there's just like a lot of good reasons to use adjusting the weights. There's 2 different ways to adjust weights. We can adjust case weight, so different observations to get different weights, and we can adjust class weights, different levels of the target variable get different weights. Most model functions that allow custom weights will rescale a non-negative vector to a probability vector, but it's best practice to always use a non-negative vector that sums to 1, just to make sure that the interpretation is right. The model will put more emphasis on avoiding training errors on larger weight observations. And it's important that I say training errors because that's what is being used during the fitting process. But remember, weights are probability vectors, or at least proportionally, and increasing the weight of one observation decreases the weight of other observations, at least somewhere. And so we have to strike that right balance. Adjusting weights does not improve model accuracy. It controls where the errors are. Adjusting weights will decrease training accuracy when compared to unweighted training accuracy. So if I adjust weights and then I take my validation and test data and I don't adjust the weights on them, when I check my statistics, my model performance, my validation statistics, my test statistics will actually degrade in almost every data set if I have a sufficient amount of data. And so that's something to be mindful of. All right, so I'm going to go through, I'm going to adjust the weights, and I'm going to adjust the weights so that the sum of the weights for bad and the sum of the weights of good are equal. All right. And so we can see that good observations have a weight of 1, bad observations have a weight of 2.33. Now, what I just said is that you should adjust these weights so that they're a probability vector, and I'm doing that right here. All right, and so now if I go through and I can, make it, some adjustments, or I can just, take a look at, the number of observations that are bad credit and number of observations that are good in the data set. And now I'm going to go through and very easily, I'm going to specify what the weights are. Each individual observation is going to have a weight assigned to it. And I'm going to, just do this. So now adjusting weights is also a good choice if I have multiple things that I'm dealing with. So let's say that in my demographic column, I didn't have the proportions I wanted. And in the target variable, I didn't have the proportions I wanted. And in a, let's say, neighborhood aspect, I didn't have the proportions I wanted. I could mathematically sit down, do the pencil and paper arithmetic, and work out weights for each individual observation to get the weights across the board that I actually want. So this is a huge advantage over other methods. Now, downsampling the frequent level. Here, I'm going to filter out some observations from the high frequency level so that I get the balance that I want. Downsampling, we filter out high frequency level observations to get the desired ratio of levels. Downsampling results in a smaller training data set, thus improving computation time. Downsampling does not take full advantage of the data. The filtered out data points are not part of model fitting, and they're not part of my validation statistics. They're not part of my training statistics. So I just lose out on those data points. Notice that the training data is being downsampled. In this particular example, I am not adjusting my validation set or test set. So if I believe that my validation set and my test set reflect the true population that I'm going to be scoring on, then I wouldn't want to adjust it. Now, I would be using downsampling if I'm in the case where, some levels are just getting choked out because they just appear less, like in that rare disease situation. And so, we have to, proceed with this, understanding that, if I make a choice on the validation and test set, there's like a compromise that I'm making, either way. And not making a choice, you're still making a choice whether you like it or not. All right, so I'm going to go through, I'm going to downsample. So I'm going to filter out the high frequency levels, and which is good. So now you'll see I have a balanced data set. All right. And now I'm going to fit my model with that balanced data set. And you'll notice that the balanced data set is a subset of the training data. Now I can upsample. So here, what we're going to do, I'm going to take the low frequency level observations, and I'm going to sample them with replacement to increase the number of times I have the low frequency level observations. Upsampled data has more observations than the original data. And so, I might have computation time increase off of this. Upsampling takes full advantage of our data while downsampling does not. Upsampling needs to occur after the train test split of our data. If we randomly split after resampling, repeated observations are almost guaranteed to occur in both training and test. And so our test statistics are not going to come from unseen data. We won't have that honest estimate. All right, so here's my training data, and you'll notice that I am upsampling it. And I just use my upsampled data to fit. And you'll notice that here, now I've repeated observations from the bad case, and then boom, I fit my model. Now for synthetic data, what we're going to do, we're going to take the minority, the low frequency level observations, and we're going to use an algorithm to generate new observations. Now, these new observations are fake observations. That's why they're called synthetic. All of the problems with imputation and fake data and come up here. So like if a lawyer was going to have the chance to attack my model, they could say, well, you made fake data up. Well, like how can I trust you when you went through and generated the data? How do I know that you didn't choose some slick algorithm to make the results look the way you want them to. And honestly, you can't really defend it. So, all the problems that you have with imputation come up with synthetic data. Also, we have the problem in relation to our train test split. So I say it's late in our list of choices for this. And what Smote does is Smote takes k points that are close to each other. They're kind of like a k nearest neighbors aspect. So k points are close to each other with the same target variable value, and then interpolates the values to create a new point. Now, with the numeric data, interpolation, makes a lot of sense. The problem with another problem with this is when I have categorical predictor variables, what happens when I have k points? Well, different approaches, different implementations will do different things. I have to look it up, figure it out from the help documentation. Not a big deal, but it's there isn't 100% true answer for that one. Now, what Rose does, Rose assumes a multivariate density on the minority classes of the predictor variables, and then uses a random number generation to create synthetic data. All right, that sounds reasonable, but still it's fake data, and I specifically don't like categorical data for this approach, because I feel like it's not really, like, if I'm just randomly generating it, random generation isn't necessarily going to connect well to the target variable. Synthetic data is fake data. As such, synthetic data is not as good as true, correct, real data, and carries all the problems with imputation. Also, synthetic data does not add new information. It only recycles information that's already present in your data, or it pollutes it. If you generate in a manner if you generate an observation that doesn't reflect the true target population, then you're polluting your data. And as such, it's just a bad way to go. All right, here I'm just going to use Smote. I'm not going to worry about Rose. Smote is by far more common to use. I'm using the performance estimation package on this one. There are a bunch of Smote packages, different implementations. I've got videos on these. Choose the one that works for you. I don't know which one's best. And you can see now I have balanced data. So it took all of the bad level data, and then use like a k nearest neighbors approach to go, hey, let's find k points are close to each other, generate a synthetic data point. K data points are close to each other, generate data points. And then I'm going to just fit the model with my data that has the original values plus the fake data. And you'll notice I'm only doing this on my training data. All right, so now let's compare the models. And this didn't turn out. I wanted to shoot. This worked out when I was doing this on our studio. So here we've got the different coefficients for the model. Yeah, so it starts here. But, we have a lot of predictor variables on this one, but here is a 5.4, and you can see the intercept is substantially different on this. I was going to compare the different values. Now let's go ahead and compute the modeled value. So I'm just going to go through, run predict, on different models, and we're just going to go through and take a look. So here we get our baseline value. So you can see that's pretty close to the original data. We have our adjusted weights. And you can see that it's pretty close to balance. We have downsample, pretty close to balance, 50-50. Upsample, pretty close to 50-50. Smote, I mean, things are not exactly that way, but overall you can see that it's close to 50-50. Now here's the actual original values, and here's our train test split. Okay. All right, so now let's compute model accuracy. And so here is my training accuracy. Here is my validation and my test. And you'll notice that training is the highest because that's the one it was built on. And here we see a bigger difference than usual on the difference between our training statistic and our validation statistic. All right, so what are our tools for handling imbalanced data? First, do nothing, right? I can always just run a model, don't have to address it. With my project, my stakeholders, that might actually be the right way to go if they're not comfortable with you tinkering with the data. Next one is to adjust weights. That is the way that I prefer. That's the way that I recommend. Next one, downsample. I'm not taking full advantage of my data, but you know what? I'm improving computation time. Upsampling. I might increase computation time a little bit. I've never had a problem with that. And I have to be more, more purposeful when I do my upsampling and I do my partitioning. And then the one that it's a tool in my tool belt, but I avoid using it is synthetic data. All right. Well, that's all I've got for you. Life is short. Do math.